Hi everyone, welcome to question 6. So in part A, we want to implement the sort edges by weight method. This is the step in our Kruskal algorithm where we want to put the edges in increasing order of their weight. So if you take a look at what this public class graph is doing, we have a nest class edge, and that will take in three things: from, to, and weight. From and to are going to represent the vertices that are the endpoints of an edge, and then the weight is going to represent the weight, which is the attribute that we want to sort the edges by. We also have an adjacency matrix. It is a 2D list of edges, edge objects. Okay, so as a reminder, adjacency matrix is going to be of size V by V, where V is a number of vertices in your graph. So let me do a really quick example. So let's say that I have only 3 vertices in my graph. I have 1, 2, and 3, and I have these 2 edges between them, okay? And this is, let's say, weight 8, and this is weight 5. And so if I want to create an adjacency matrix for this graph, I know that the dimension of my matrix is going to be 3 by 3. And this is going to represent my vertex 1, vertex 2, vertex 3. This is going to represent vertex 1, 2, and 3. Okay, and so in each of these 9 cells, I put a 1 if there is an edge between the 2 vertices corresponding to that row and that column. Okay, so for example, in this first cell, the upper leftmost cell, is there an edge between 1 and 1? In other words, is there a self loop, right? Something that looks like this. Well, in this case, it's not really directed. So let me delete the arrow. Something that looks like this, right? It's a self loop. Well, we don't have any self loops in this graph. So actually all of the diagonal entries are going to be 0, all the main diagonal entries. And let's look at this one. Is there an edge between 1 and 2? Well, yes, right? It has weight 8. And so we can put a 1 here, and we can also put a 1 here. It's symmetric because we're assuming that it's an undirected graph. And similarly, for the edge between 1 and 3, we know that we'll put a 1 here and also here, and then everything else is going to be 0 because you only have 2 edges in our graph. And you can do the same thing for a directed graph, but for MST algorithms, Kruskal and Prim, it will be for undirected graphs. Okay, so this is a little bit of a different implementation though, because instead of the elements of our adjacency matrix being integers, we actually have them being edge objects. But these edge objects are really not anything intimidating. Really what it would look like, let's say that I'm actually implementing, let me just show you for this cell, okay? So if I have my elements of this adjacency matrix edge objects instead of integers, then this is really gonna look like an edge object where to, or let me start with from, as in the code. It takes a while for Zoom to upload or update my editing. Sorry, I'm gonna go out of the box a little bit. But basically, this is all that it's gonna be, right? That's the only change. It's just a pointer to an edge object instead of an actual primitive value. But same thing, right? Let's say I go from whatever the row is to the column. So the row is here 2, and the row is 2 and the column is 1, okay? And let's say the weight is 8 because that's how it is in our graph, right? So that's really all there is to it. So if we have all of this information, right, if we just access the cell and we see if there is an edge object, and if there is, then we use that to first retrieve its weight value, right, because that's how we're going to sort these edges by, and then actually sort these edges by calling the sort. It kind of makes it pretty clear to me that I just need to go through my adjacency matrix, and using this IJ, I can index into it, see if it has an edge object or not. And if it does, then I just add it to my array list of existing edges in my graph. And then at the end, I call sort, and then I just return the sorted edge array list, right? Okay, so I know that both I and J are going to have their limits be determined by the adjacency matrix length, right? Which is really just the number of vertices, but you don't have access to the number of vertices. So you will have to use the adjacency matrix length. And so let's say that I is going to go from 0 and then I is less than adjacency matrix dot length. And make sure that you specify that it's only dot length instead of dot length parentheses, because that's only for strings, right? You should not have parentheses for lists. Okay, and now what is j going to be? Well, we could technically say int j equals 0 and then j also less than adjacency matrix dot length. But as we saw in the example with the 3 vertex graph, the main diagonal is always going to be 0, right? Because we're not going to have any self loops in our graph. And so we can just kind of optimize it a little bit by saying, all right, we're just going to start at I, whatever I is. Okay. And the other thing, actually, this is not really an optimization on the main diagonal. It's really an optimization on the fact that the adjacency matrix for undirected graphs is going to be symmetric, right? Because an edge between 1 and 2 is the same as an edge from 1 to 2 and from 2 to 1, right? And so what if we just find the value of this cell, there's no reason for us to look inside this cell as well, because we know that they're going to hold the same exact value, right? So we can just start from I, and we can even say that we don't have to start from I, we can start from I plus 1, because again, the main diagonal is always going to be 0, assuming that we don't have any self loops in this graph, right? And that's what it says here. Okay. And then at the very end, we need to sort these edges. And so sorting is going to take in a function that we want to apply to what we're sorting, right? So the function is going to be in the form of a lambda. Okay, remember how lambda works in Java. So we take in parameters. In this case, we have to take in 2 things. So let's say we're taking 2 edges, E1, E2. And then the body of this lambda is going to be after an arrow. And basically, what is the criteria for determining which one is greater? Well, we need to look at their weights, right? So we could do something like E1 dot weight minus E2 dot weight. Okay, and that is it for this question.